welcome to our presentation. My name is Oponkese Galvin and my partner is Saki Atumbo, and we are both second year students in petrochemical engineering. And today I'm going to be showing you a project we built using MATLAB for our computer applications course. And a crude oil refinery stream analyzer coded entirely in MATLAB. This tool simulates what happens when oil enters a refinery, from characterizing the crude to analyzing its product fractions, all the way to checking how a reactor behaves at different temperatures. So without wasting much time, let us get into it. So this is the code for application, and it's about 305 lines of code. Yes, 305 lines of code. So you can open the command window to interact with our app. To launch the application, all I have to do is type the name of the file in the command window, which is Refinery Analyzer. So in my command window, I'm going to type Refinery Analyzer to start the application. And just like that, the application opens. And the title is Crude Oil Refinery Stream Analyzer, Atmospheric Distillation and Stream Properties. It gives 3 models to choose from. Here we have model 1, which is crude oil characterization, model 2, distillation cut stream properties, and model 3, reactor feed, and 0 to exit the application. We are going to go through all the 3 of them, but let's start with model 1. So we come below it, enter choice 1 for model 1, and immediately it opens. And here's the title, Crude Oil Characterization. Okay, this is where everything begins. In a real refinery, before you do anything with crude oil, you need to understand what is inside it. That is exactly what this model does. And the first thing it asks for is the crude feed rate in barrels per day. And this is simply how much of the crude oil is flowing into the refinery every day. So I'm going to use 10,000 barrels per day, which is typical for medium-sized refineries. So we are going to go to that part and input 10,000. Press enter. And next, it asks for the API gravity. API gravity is a number that tells you how light or heavy the crude oil is. The higher the number, the lighter the oil. And water says that's 10. This shows that oil will always be above 10 because oil is lighter than water. When water and oil is in the same container, water is always above oil. So the values for the API gravity of any crude oil should be always higher than 10. And the ranges for it are, when it is 40 plus, it is light crude oil. When it's from 30 to 40, it is medium crude oil. When it is 20 to 30, it is heavy crude oil. And when it is 20 and below, it is extra heavy crude oil. These are the ranges for the API gravity when it comes to crude oil. So let us input 35. Immediately we get our input from giving it those 2 information. So here's the result for the crude characterization. So from those 2 inputs, it gives us our feed rates, our crude type, which is medium crude. From the ranges I told you, it is matching perfectly. The API gravity, which we inputted, the specific gravity, your density, your volume, your mass flow. All this information are given to you from the 2 inputs you give first. Then we come here to cut yield flow, which is in barrels per day. So for light naphtha, which is one fraction which you get, they are saying you get 5% of light naphtha. And for heavy naphtha, which is also another fraction you get 12% of heavy naphtha. And for kerosene, you get 13% of kerosene. For diesel, you get 20% of diesel. And for the residue, you get 45%. And it also gives you your Watson K factor, which is 11.89. And when the Watson K factor is greater than 12, the crude oil is paraffinic, meaning it is easy to process and it's valuable. And when it is less than 12, it is naphthenic or aromatic, which means that it is difficult to process and it gives more residue as a product, and it is not really valuable because it doesn't give you more of the product you are seeking for. And from this information, we can see that from here, realize that all the other fractions are small portions, but the residue is in a higher portion, which is 45%, because the Watson factor is 11.89, showing that it's naphthenic or aromatic. And from this information, they also tell us the cracking potential, high significant upgrading required, telling that you need more heat to be able to get all the components that you want. So this is the information model 1 gives you. Just from the crude oil, you are able to dig out. If you are working in a company, in a refinery, this is the way model 1 assists. And to specify something, the crude API gravity and some other values which I'm giving out are values that are gotten in a lab. When the crude oil comes, the first thing they do is to send the crude oil to a lab where many things are tested and values like the API gravity are given. So from that, we can go to the next step, which is model 2. So I'll input 2 and press enter. Okay, so model 2 says distillation cut stream properties. It's showing us the available cuts, which are the 5 fractions of the crude oil we will get from this crude oil. And what it does is that when you select one of these fractions, you can look at the stream properties. The properties when it is flowing through a pipe after it has been gotten as a fraction. So let us pick one. For this example, we are going to pick 3, which is kerosene. And the first thing they're asking for is the flow rate of this cut. And for our model 1 result, we know that kerosene is coming out at 1,300 barrels per day. So I'm going to input 1,300. And secondly, it's asking for the pipeline internal diameter in inches. In a rail refinery, this comes from the engineering design drawings. For a kerosene product line, 6 inches is the standardized size. So I'll enter 6. And thermodynamic viscosity. This tells the app how thick or thin the fluid is. Kerosene is slightly thicker, around 2 centipours. This value comes from lab tests done on fluid. So I'll enter 2. Okay, so it's giving us our results for the stream properties of kerosene. So it's giving us the API gravity, which is given 45 degrees. It's giving us specific gravity, density, average boiling point, Watson K factor, which is still below 12, showing that it is difficult to process. And for typical use of kerosene jet fuel, it's giving us the flow rate, pipe diameter, which we gave, mean velocity, the speed at which it is moving in that pipe, and a Reynolds number, which shows that the flow region is turbulent, meaning the fluid is moving in a chaotic, well-mixed manner, which is actually normal or healthy for petroleum pipelines. So it's giving us a warning. Velocity is less than 0.3 meters per second. Wax deposition or settling risk. Because it is moving at a very slow rate, there's a risk of it settling and becoming wax deposits in the pipe. So if the engineer gets a warning like this, certain changes can be made to avoid this. So this is also how Model 2 can assist the petrochemical engineer. So we are moving to Model 3. So we input 3 to move there. So finally, Model 3. Reactor feed Arrhenius kinetics. Before sending any petroleum fraction into a reactor, the engineer needs to know how the reaction rate changes with temperature. And this uses one of the most important equations in chemical engineering, which is the Arrhenius equation. It shows us the reaction. Okay, so it shows us the equation here. This is the equation. So with this, we are going to input our values, which will ask us in the process to input it, and it is going to give us the rate change. So the temperature of the reactor, it is currently running at 300 degrees Celsius. The rate constant K1 at that temperature 0.0. We make it 0.05. And this comes from the lab kinetic experiments. So 0.05. As said, some values are gotten from the lab. And the activation energy, we are going to use 80 kilojoules per mole. This is the minimum energy molecules need before they react. 80. Now it's asking for the new operating temperature T2. Let's say the reactor temperature drops to 250 degrees Celsius, and we want to know how badly that affects us, the reaction. So let's make that 250, which is a temperature drop. Okay, so here are our results for the Arrhenius analysis. Okay. So at 250 degrees, at 300 degrees, the rate constant is 0.05. At 250 degrees, it drops to 0.0243. And it's saying that when that drop happens, the rate change is 0.20 times slower. So it's telling us that if the reactor is already at 300 degrees Celsius and there's a temperature drop, the reaction is going to be 0.20 times slower. And it's also saying that the half-life at T1 is 13.8629 seconds, and the half-life at T2 is 68.977 seconds. So it's saying that at T1 it takes 13.8629 seconds for half of the reactant to be consumed, and when the temperature is changed to T2, it takes 68.9773 seconds for half of the reactant to be consumed. So this is saying that the reaction is going to be much longer if the temperature drops. So when it gives such information, the engineers can check and monitor the temperature drop, so that if it goes beyond the range which they've already studied how it affects the reaction, they can adjust it so the reaction happens at the rate which they want it to. But it also gives us another feedback. Rate change is within manageable operating range, meaning that it's not dangerous for it to drop to that temperature, just that it will become slower of a reaction, but it won't become dangerous for the system. So that we can go back, press enter, and it sends us back to the menu. So that's the 3 models that it performs. If I press 0, it takes me out of the application. Goodbye, thank you for using Refinery Analyzer. Yes. And that's the end of the crude oil refinery stream analyzer. In under 15 minutes, we went from raw crude oil all the way through characterization, product fraction analysis, pipe safety, and reactor kinetics. all three models connected together to tell one complete engineering story. What I love about this tool is that it's not just about getting numbers, it's about understanding what those numbers mean. Whether your pipeline is safe, whether your reactor can handle a temperature drop, what product your crude will actually give you. And this was built entirely in MATLAB with no external toolboxes, just clean engineering logic and the equations we study every day in class. If you found this useful, please give a thumbs up and subscribe to the channel for more engineering content from my other classmates. Thank you. Bye.